Hi class. Today we're going to look at section 5.2, but before you start this lesson, please make sure that you have a protractor. Also, a note card would come in handy. You can use a compass if you would like to, and you will also need your sheet, the chart that has the triangles in there and some blanks to fill in. Those are the things that you will need for this section. If you don't have those, pause this, go get them and come back. Once you've got all those things, then you can get started. Section 5.2, we're going to continue learning about the special types of segments. We're going to work on the final two segments here. So we're going to take the chart. Play the switcheroo game. All right, take that chart and we're going to fill in two new sections, one at a time. The first one we're going to start with are angle bisectors. Angle bisectors. These bisect angles. Angle bisectors. They're going to bisect the angles in your triangle. Now, once again, we did do this earlier with the compass. So you can go back to those videos and you can look at how to create angle bisectors with the compass. It's actually pretty straightforward and pretty easy. Some students like to do it that way because it's just real quick. They don't have to measure anything. We do have the videos though on YouTube about how to construct those angle bisectors. But if constructing the angle bisectors just wasn't working for you, you can do this with your protractor. All right, so we're going to look at how to create an angle bisector. You can take any of the angles. It doesn't matter which angle you take. We're just going to measure it and we're going to cut it in half. Okay, I think I'm going to do that with the largest angle just because it might be a little bit easier for me to see. But you can do that with any of the three angles. Notice I'm going to line that up with the center of my protractor right at the vertex of that angle. And I've also got the line on my protractor lined up exactly with that side of the angle. And I'm going to look at where does that side go. I might use my note card to help me. Okay. Put my note card along here so I can line that up and it helps me see a little bit better what the actual angle is. Okay, so my angle is starting at, let's see if I can take that. All right, my angle is starting in this direction. So I'm going to start at 0 as I go on this side. So here's 0. I'm going to work my way up the small numbers, 10, 20, 30, all the way up 70. It looks like 75. So it looks like that angle is 75. And in order to bisect it, I need to divide that in half, which is going to be 37.5. So I'm going to look for, here's 35, 36, 37. So 37.5 is going to be right about there. I'm just going to make a little dot. Make a little dot right there. That's at about 37.5 degrees because my full angle was 75 degrees and I want to cut that in half. If my full angle is 75 and I cut it in half, that's 37.5 degrees. I put a little dot there. With that dot, now I'm going to come back. I can take my ruler, I can take the side of my protractor, I can take my note card, any of these things. I'm going to line up the vertex that I just measured, that angle I just measured. I'm going to line that up with the dot that I made down here. And I'm going to draw in that angle bisector. I only need it to go through the triangle. I don't need it to come all the way down to the dot that I made. Okay, so there is my angle bisector. Bisecting means that it's cutting something in half. So this angle is congruent to this angle. If I were to measure each of these angles, each of the angles up here should measure 37.5 degrees. All right, so angle bisectors. Now I could do that for each one of these angles. I could measure this, I could cut it in half, and figure out where that line needs to get drawn in. I can do that over here too. Measure this angle, figure out what half of it is, and draw in half of it. Again, the compass is a great tool for that because you don't have to measure anything. If you're having a hard time trying to figure out the measurements from your protractor, maybe go back and take a look at the construction video, Bisecting Angles. That'll be in the Network Geometry YouTube channel. But that can help you out with these problems too, and you won't have to worry about measuring anything. All right, so angle bisectors. What are we going to do with this? Angle bisectors. The first thing that we need to know about them is their definition. So let me move this up, move this into place. Angle bisectors. They are segments that bisect one of the angles. That's pretty straightforward, right? So angle bisector is a segment that bisects one of the angles. And you will get two congruent angles once you construct that. Now, with our chart, as we did in 5.1, we also need to find the point of concurrency. In other words, if I made all three angle bisectors and drew those all in, those would all meet in my triangle. I need to know what's the name of that point of concurrency. And that is the incenter. Let me get this up here so we can see all of that. All right, so the incenter, that is the common point of the angle bisectors, the point of concurrency, or the common point of the angle bisectors. The incenter will always be inside the triangle, always, always. All right, so if we were to construct or measure all of those angle bisectors, draw those in, we would find that they meet somewhere inside of the triangle. This is the incenter. You're going to need to be able to match up incenter and angle bisectors. You'll need to remember that those two go together. Okay, the incenter will always be inside of the triangle, the point of concurrency, always inside. And then the special relationship. The incenter is equidistant from the sides of the triangle. Now that's a little bit of a tricky one here. And I'll talk to you about that in just a minute. All right, the incenter is equidistant from the sides of the triangle. Now that doesn't mean these little marks here. It doesn't mean these solid marks here. It doesn't mean that it's this distance, this distance, this distance. Okay, the shortest distance is a perpendicular line segment. That's what will be the same. All right, the shortest distance will be a perpendicular line segment. So a line segment from the incenter that is perpendicular to each of the sides of the triangle, that's the distance that will be the same. I'm going to come back in a minute and show you what that looks like, but I want us to fill this in on our chart first, and then I'll give you a little bit more specific drawing and showing you what I mean by that. All right, so coming back to our chart, we're looking at the point of concurrency. And then if the point of concurrency is inside on or outside the triangle, and then the point of concurrency special relationships. I'm going to zoom this out so you can see this a little bit better. For angle bisectors, we're going to follow it all the way down here. Where the angle bisectors meet, that is called the incenter. The incenter is always inside of the triangle, always inside of the triangle. And the point of concurrency, the special relationship there, that point, the incenter, is equidistant from each side. All right, that incenter, that point, is going to be equidistant from each side, the same distance to each side of the triangle. But once again, that's going to be a perpendicular distance. Let me show you what I mean. Okay, I'm going to zoom in on this. Zoom in on this triangle, and I'm going to use my note card because I know that I get nice perpendicular lines from my 90-degree angles, right? My corners are always 90 degrees. So what I'm going to do is line up the side of my triangle with that in-center point. Now for this purple one, it looks like that might be about 90 degrees. Okay, that won't happen with all of them. So then I go to the green one, or where the angle bisector is from that green angle, and I line these up. I'm going to draw in that perpendicular distance right here. And then I'm going to do one more down at the bottom. Now these are pretty close to the angle bisector. It won't always be this way. It depends on what type of triangle you have. You'll see especially a difference if you've got like an obtuse triangle or a triangle where your sides are very much scalene. This triangle is not too far off from equilateral. The sides are kind of close to the same length. The angles are probably kind of close to the same measure. And so you're going to see these come pretty close to lining up. But the more scalene your triangle is, the more of a difference you'll see between where the angle bisectors, where the lines for the angle bisectors go, and where these perpendicular dotted lines are. Okay, so these are your perpendicular distances, the ones that are on the dotted lines. Those distances are the ones that are congruent. Okay, it's the same distance from the in-center to this side, to here, and to here. All of these dotted line segments would all be the same length. All right. When you see this in your book will most likely draw the angle bisector up to the in-center, up to the in-center, up to the in-center, and then it will stop right here at the in-center. Okay, and then your book will show these dotted lines to show the perpendicular distance from the in-center to the sides of your triangle. So when you're going through the homework, that's what you're going to see. All right, the last type of segment that we're going to cover in this section is called the median. Okay, median. And a median is a segment whose endpoints are the vertex of an angle and the midpoint of the opposite side. All right, so it's going to go through the vertex and the midpoint of the opposite side. Now, if you're going to use your compass to try to construct this, you would be constructing, figuring out where the midpoint is here, basically by going through the same steps as you would for the perpendicular bisector, but only just to find that midpoint right there. Instead of drawing in the whole segment, you would just draw in that midpoint right there. So you'd use your compass to make an arc from this point, make another arc from this point, and then you'd line up a straight edge. It can be a ruler, a note card, anything straight between those two arcs, and you would just mark the midpoint. So that's what you would do over here for a median if you were going to use your compass to find the midpoint. The other way to find the midpoint is just to grab a ruler. All right, and it looks like right about there. And so you would connect that vertex to the midpoint of the opposite side. So that right there is the median. Since this is the midpoint of this side, the middle point means that it's dividing this side into two congruent parts. So it will be bisected. We are going to have two congruent parts down here, and it goes up to the vertex. Okay. The median, again, it is a segment whose endpoints are the vertex and the midpoint of the opposite side. The endpoints are a vertex and the midpoint of the opposite side. Now, again, on the chart, we've got the points of concurrency, we need to know if that's going to be inside, on, or outside of the triangle, and then any special relationships. All right, so here's what we have for the medians. Where all of the medians intersect, we get the centroid. So the centroid is the common point of the medians. This point right here where you see the letter T, that is the centroid of this triangle. And the centroid, this is the special relationship, the centroid is 2/3 of the distance from each vertex to the opposite side's midpoint. What that means, if I'm going to look at this green segment right here, it means that the centroid, this point right here, is 2/3 of the way, and this is 1/3 of the way of this whole line segment here. So whatever this distance is of this green line segment that you see, from B to T takes up 2/3 of that distance, and from T to Y takes up 1/3 of that distance. Same thing with the blue line segment. Whatever that segment's length is, from C to T takes up 2/3 of that length. T to Z takes up 1/3 of it. Okay, same thing here with the purple one. So we're going to go back to the chart. So we're going to finish filling in the chart here. And under median, the point of concurrency was called the centroid. And you will need to be able to pair median and centroid together. You will need to know that where the medians intersect, that point's called the centroid, those two to go together. Okay, and the centroid will always be inside of the triangle. Centroid will always be inside of the triangle. Whenever you draw all of your medians in, that point will always be inside the triangle. Will not be on it or outside of it. Will always be inside. And then we've got that special relationship down at the bottom. The special relationship is that it is 2/3 of the way from the vertex to the opposite midpoint. Okay, so 2/3 of the way from the vertex to the opposite midpoint. Two-thirds away of the vertex, 2/3 of the way from the vertex to the opposite midpoint. So we can say it divides the median 1/3 and 2/3. It divides the median into two parts. Okay, it divides the median into two parts. One part is 1/3 of the median, and the other part is 2/3 of the median. Okay, so it divides the median into two parts. And let's take a look at an example of a problem that you might encounter in the homework that's going to deal with this. Okay, because I know that that can sound really confusing. So I want to give you an example of how you would handle a problem like that, what it would look like. All right, so here's an example. Let's zoom in, get it centered. All right, so this is an example of something that you would likely see in your homework. First of all, it's going to tell us that T is the centroid of ABC, triangle ABC. So a problem like this, with them telling you that it's a centroid, one of the first questions they might ask you is, what type of segments are in this triangle? And you'd have to remember that centroids go along with medians, and you would know that each of these segments in the triangle is a median. Okay, so the next thing, if AX equals 1, so if this whole segment right here equals 1, then here's how this segment gets broken up. AT would be 2/3 and TX would be 1/3. So if this whole thing right here were, let's say, 1 foot, right? Then AT would be 2/3 of a foot and TX would be 1/3 of a foot. Whatever your units happen to be. All right, here's another example. If you're told that YB is 15, whatever the units happen to be. YB is 15. They want to know how long is BT and how long is TY. Okay, BT is going to be 2/3 of that whole distance. TY is going to be 1/3 of that whole distance. All right, if the whole distance is 15, here's what that looks like. Then BT is 2/3 of 15, and TY is 1/3 of 15. Well, sometimes 1/3 is easier to do in our head. So 1/3 of 15 is 5. And so 2/3, that would be 5 and 5. That's going to be 10. So if this whole segment here, BY or YB, if this is 15, this part right here is going to take up 2/3 of that. So this part right here, this segment's going to be 10. And this segment here is going to take up 1/3. In other words, it's going to be a length of 5. Okay. Let's practice that with another one of these. If CZ is 12, then what are CT and TZ? If CT or CZ is 12, if this whole segment here is 12, then how long is CT and how long is TZ? Well, again, remember, from the vertex to that centroid, that's 2/3 of the whole distance, and this is 1/3 of the whole distance. If the whole distance is 12, this top part here is 2/3 of 12. This bottom part here is 1/3 of 12. All right, 1/3 of 12, that's like 12 divided by 3. Okay, that's going to be 4. And then CT is going to be double that, twice as big, because it's 2/3. 2/3 of 12. Okay. Try this one. This one's a little bit different. Instead of giving you the whole segment, in this one, they might just give you part of the segment, and then you have to figure out the rest of it. So TX is 3, and they want to know how long is AT and how long is the whole segment AX. All right, well, the relationship here, whatever this is, the shorter part here, the longer part's going to be twice as big because this is 1/3, this is 2/3. Okay, if this is 3, this is going to be double it. That means that AT is going to be 6. And if this part right here is 3 and this is 6, then the whole segment altogether will be 9. All right, and I've got one more here. This one's a little bit different because we have some algebraic expressions in it. Your book will throw this at you occasionally, so be prepared for it. Now in this one, they're saying that AZ, now we're on the outside of the triangle, so also watch for that. AZ is 2x minus 3. ZB is x plus 1. So they want to know what's the actual length of this, not as an expression, but as an actual number. All right. Remember that the centroid is made up of medians. And if CZ is a median, that means that it goes from the vertex to the midpoint of this opposite side. A midpoint is going to divide that side into 2 congruent parts, 2 equal parts. So whatever AZ is, ZB will be equal to that. Whatever AZ is, ZB will be equal to it. So this is how I would start out my problem. Now I'm going to substitute in the expression. Instead of AZ, I'm going to write 2x minus 3. And for ZB, I'm going to write x plus 1. Solve for x. So let's see, I think I'm going to get x over to this side because my x's are bigger over here, so I'm going to subtract x. And I'm going to add 3 to both sides. I can do this at the same time. Adding 3 to both sides is going to help me just get my x's on this side and my non-x's on this side. My x's are gone over here, 3's gone over here. I'm going to get 2x minus x. I'm going to have x equals 4. Now, is that my final answer? No, because I wasn't asked to just solve for x. I was asked for what is the length of AZ. So I have to take x equals 4 and plug that back in here. So AZ, 2x minus 3. Now I'm going to put a 4 in here. 2 times 4 minus 3. So I've got 8 minus 3. So AZ is going to equal 5. So if this part here is 5, then you'll know this part here is 5, and the whole base of this triangle from A to B would be 10. All right. Those are the types of problems that you're going to see that they can ask you about when you're dealing with a centroid. So be prepared for that. Come back to this example. Watch this if you need to, or better yet, pause this and copy down what you see here in your notes so that you can just flip back to your notes instead of having to watch the video. I'm going to put the chart up one more time. We'll zoom out. So in case there was anything else that you needed to catch from this chart, you can get that. And again, in section 5.1, we worked with the perpendicular bisectors and the altitudes. In 5.2, we've got the angle bisectors and the medians. All right, you guys will be responsible for being able to remember the point of concurrency and the type of segment. So make sure that you can match those words up. You'll be responsible sometimes for drawing these in. Make sure that you can draw them in. Again, you can either use a compass, you can use your protractor, a ruler, even a note card is good because the corners are 90 degrees, so you know that you'll be able to make your perpendicular line segments in those places. You'll need a protractor at the very least for angle bisectors. You can also use a protractor to do 90-degree angles. A compass also works very well. So you can go back to the videos if you want to be reminded about how do we bisect a side, how do we bisect an angle, how do we find the midpoint of a side. Those things are all in those other videos using the compasses, doing the constructions, okay? And those can be very easy once you get the hang of them. So don't rule it out as an option. It can work pretty well for you, all right? Sometimes you will be given a picture and you'll be asked to identify what special type of segment you were using. Sometimes you'll be given a picture with the point of concurrency, and you'll have to figure out based on just the picture and the point of concurrency, what kind of segments am I dealing with, and remember the special relationships that those points of concurrency have in the triangle. So do the best you can with this, and let me know what questions you have.